So here we'll do just a little bit more review and then we'll continue our work with limits. First, I want to remember how absolute value is actually defined. So absolute value of x is actually a piecewise defined function. It says absolute value of x is equal to x if x is greater than or equal to 0. So this says if x is 0 or a positive number, then that value, that number, just stays the same. So absolute value of 5 is just 5. But then we know, okay, what happens if you take absolute value of negative 5, right? Then you change the sign. So the way we do that mathematically is we just multiply by a negative 1. So negative x if x is less than 0. So this says, hey, if x is less than 0, you change the sign on whatever that number is. So if you have a negative number, you just change the sign. That's what absolute value does to it. So here is the graph of h of x equals absolute value of x divided by x. We're going to take a look at this and evaluate each limit. I just want to talk about how to come up with this graph, though, just because it is a little bit tricky to graph it. What I would do, honestly, if you're not sure where to start, is I would just take some points and plug those in and see what happens. So, for example, let me do this in blue here. If I had chosen, say, x equals 1 and plugged that in, h of 1 would be absolute value of 1 divided by 1, which is 1 divided by 1, which is 1. So that's how I get this point right here. Maybe if I wanted to choose, say, x equals negative 2, if I take that number and plug it in, h of negative 2 is absolute value of negative 2 divided by negative 2. So if I take absolute value of my numerator, I get a positive 2 divided by a negative 2. Well, if I divide these two, I get a negative 1, which is where this point comes from. And you can do that with all sorts of numbers, but the one number I do want to talk about in particular here, because this graph doesn't do a great job of showing it, is 0. If x is equal to 0, so if I take 0 and plug that in, I end up with absolute value of 0 divided by 0. And hopefully you look at that and are already concerned. Absolute value of 0, that is 0 divided by 0. If we're talking about the value of the function here, so if we take a number, we plug it into our function, and we end up with 0 over 0, in this case, we will say that our function is undefined or does not exist. Undefined or does not exist there at x equals 0. So really, if I wanted to make my graph more accurate, I really should have open circles right here at 0, 1 and 0, negative 1 to show that, oh, the graph actually doesn't exist there. If you do use programs, so I'm using a program here called Desmos to make most of my graphs, or if you use, say, like a graphing calculator, technology doesn't always do a great job of displaying holes in your graph, so you might need to just be a little bit careful about those. So here I'd like to just look at some limits of this function. Here in part A says the limit as x approaches negative 1. So here, as I approach negative 1 from each side, here's 1, here's the other. It looks like they're pointing at the same y value. They're both pointing at this point right here, which has a y value of negative 1. So, okay, the limit then must be negative 1. Limit as x approaches 1 of h of x. So here I'm talking about, oops, let me erase some of this stuff right here. Limit as x approaches positive 1 this time. So here, as I approach positive 1, I'm going to think about tracing my function from each side. They're both approaching this point right here. Well, that has a y value this time of positive 1. Part C, though, this is, of course, anytime there's something interesting in your graph of the function happening, that's usually the part we want to look at. Limit as x approaches 0 of h of x. So as x approaches 0 from each side, Here, if I approach from the left-hand side, I'm approaching this guy right here. I'm approaching a y value of -1. Here, if I approach from the right-hand side, I'm approaching that y value of +1. In the last video, we said, you know what, if the two parts of your graph, right, if the left part of your graph doesn't point at the same spot as your y or your right part does, then in this case, we would say that this limit does not exist or is undefined. So we'll just say does not exist. But it feels to me like we can be more specific about what's going on here. So this leads us to our next definition here. So here, we're going to talk about left and right-hand limits, or sometimes these are called one-sided limits. So let's talk about the left-hand limit first. Left-hand limit says limit as x approaches c from the left. So this little minus sign is really all you have to know, that all there is to tell you that, hey, we're looking at the limit from the left-hand side. So the limit of f of x as x approaches c from the left is equal to k means that f of x gets closer to k as x gets closer to c from just the left-hand side. So we're just kind of looking at one of our arrows rather than two. We're just looking at the coming at or approaching that x value from the left-hand side. Right-hand limit defined very similarly. Again, there's only this little plus sign here to tell us that you're looking at a right-hand limit and not a left-hand limit or a two-sided limit here. So a right-hand limit here is the limit as x approaches c from the right-hand side of f of x is equal to L, means that f of x gets closer to L as x gets closer to c from the right-hand side. So again, we're just talking about kind of approaching it from that right-hand side here. And then this theorem here, well, let's come back to that theorem here. I actually want to go back and look at the left and the right-hand limits. So if we go back and revisit this example here, if I wanted to talk about, okay, well, at 0 we said our limit does not exist, but let's talk about the limits as x approaches 0 from the left-hand side of h of x, and then we'll also talk about the limit as x approaches 0 from the right-hand side of our function. So here, if I'm approaching 0 from the left-hand side, we said, oops, and you know what? I erased the holes in my graph. I want to make sure that I include those. There we go. So here, if we approach 0 from the left-hand side, so okay, here is x equals 0, right? Here is x equals 0. I'm going to go a little bit to the left, and you can move 1 unit away. Ideally, we should still be very close to that number, so even 1 unit away for me is usually too far away, but if you need a starting point, that's not a bad place to start. So I'm going to move so that I'm a little bit to the left of 0, and then I'm just going to trace my graph, and I'm going to say, okay, if I follow that graph back to 0, if I follow this graph back to 0, what y value are we pointing at here? So the limit as x approaches 0 from the left-hand side in this case, that is equal to -1. Because that's what the left-hand side of my graph, right? If you kind of visualize that arrow is pointing, that left-hand side of my graph is pointing at -1. Similarly then, for the right-hand limit, so okay, here is 0, I'm going to move a little bit to the right here, and I'm going to say, okay, where's my function here at 1? It's right here. And as I trace my function back towards 0, as I follow this blue arrow, I want to say, okay, where is that blue arrow pointing here? Well, my blue arrow is pointing at +1 there, so I can say that the limit as x approaches 0 from the right-hand side, whoops, I forgot my function, h of x is equal to here, +1. So the left-hand limit is -1, the right-hand limit is +1. So this allows us to give a little bit more detail about those limits that do not exist. We can kind of talk about, okay, well, the limit might not exist, but the left and the right-hand limit might exist. If I ever talk about just the limit here, assume that I'm talking about this guy, which I'm going to call this the two-sided limit here. But if I'm talking about a one-sided limit, I'll go out of my way to say, hey, we're talking about the left-hand limit or the right-hand limit or the one-sided limit, something like that here. But if I just say the limit, then we're talking about the two-sided limit. And this actually gives us a really nice demonstration here of that theorem that I wanted to come back to, and here we'll come back to it. It says, for a limit to exist, the left and the right-hand limits must be equal. So the kind of the math jargony way of talking about this says the two-sided limit the limit as x approaches c of f of x is equal to L if and only if the limit from the left-hand side, the limit from the left-hand side of c of f of x is equal to L, and so is the limit from the right-hand side. So if the two one-sided limits are equal, then I know exactly what the two-sided limit is. It has that same value. But if they're different, I know that does not exist. Excuse me, the two-sided limit does not exist. So if I kind of look backwards here, look back at this problem that I was just referring to, here the left-hand limit was -1, the right-hand limit was +1. If I know that piece of information and I don't know anything else, I don't even know what the graph looks like, I can then say, you know what, the left-hand limit is different from the right-hand limit, which means that the two-sided limit does not exist. And we'll be using that quite often here in this next example. So let's look at another example here. I've got this lovely function here, f of x, and I want to look at the limits here, and I'm going to pick a few different x values here, and I'm going to talk about the left-hand limit, the right-hand limit, the two-sided limit, and then the value of the function. So these are kind of the four things that we need to be able to talk about when we're looking at the graph of a function. So let's start with 0. So this says, let's look at 0 from the left-hand side here. So if I approach 0 from the left-hand side here, if I approach 0 from the left-hand side, my arrow is pointing at, well, and y value of also 0. So okay, I can say that my function has a has a limit of 0 from the left-hand side. If I look from the right-hand side, now limit as x approaches 0 from the right-hand side. So here, okay, here it looks like if I look at that blue arrow is also pointing at a y value of 0. It's pointing at this point right here. So okay, that means that the right-hand limit is also 0. So you could look at your graph and you could say, well, both sides are pointing at the same y value, so I know that this limit is also going to be 0. Or, remember, you could say, you could actually just cover up this entire graph. You know, I don't even have to look at that graph. I could just look at this piece of information right here. I could say the left-hand limit is 0, the right-hand limit is 0, so that means that the two-sided limit is 0. So I could give you a problem. I could say, okay, I know that the left-hand limit is 1, the right-hand limit is 1. What do we know about the two-sided limit? F of 0, then, that's just the value of the function. Here in this case, there's no holes or anything crazy like that. We just have a point right there. So in this case, f of 0, well, also equal to 0. Next, let's look at +1 here. So let's investigate the behavior at +1. So let's look at the limit as x approaches 1 from the left-hand side first. So here is x equals 1. If I approach 1 from the left-hand side here, I want to say, okay, where's that arrow pointing at right there? So that arrow is pointing right here at this y value. Looks like that has a y value of +2. So I have my left-hand limit. My right-hand limit then, limit as x approaches 1 from the right-hand side. I'm going to move a little bit to the right, and this time I'm going to trace my function. I'm going to say, okay, now this time, what is the right-hand side pointed at right here? Well, the right-hand side here is pointed right here at this open circle, which looks like it has a y value of -1. So when it comes to looking at the two-sided limit, you could look at the graph of your function, absolutely. Or you could say, you know what, I know that the left-hand limit is 2. I know that the right-hand limit is -1. The two one-sided limits, they're not the same. Sometimes I'll say they do not agree. The left and the right-hand side do not agree. So in this case, I would say, well, the two-sided limit then does not exist. I don't even need to look at the graph. If I have the left-hand limit and I have the right-hand limit, I can figure out the two-sided limit without even looking at the graph, which is a really, really nice thing to be able to do. So, okay, let's erase this here just so that we can look at our function without any distractions. F of 1 then, so f of 1, what's the y value of our graph at 1? Again, remember we're not looking at any open circles because that shows that there is a hole in the graph. I do, however, have this closed circle right there at 1, 2, so my function has a y value of +2 there. Lastly, we'll look at the behavior of our graph at x equals 3. So here at x equals 3. So let's start with the left-hand limit first. Here is x equals 3. And as I approach x equals 3, here I'm going to start on the left-hand side. I'm going to say, okay, what y value are we approaching as we get closer and closer to x equals 3? Well, it looks like we're approaching this open circle right here. So here we have a y value, it looks like, of -2 right there at that hole. So as we approach 3 from the left-hand side, we have a y value of -2. If I look at now 3 as, the limit as x approaches 3 from the right-hand side. So here, again, here is x equals 3. Let's scroll back up here. Here's x equals 3. And here I'll start a little bit on the right-hand side of 3. And as I trace my function and get closer and closer to 3 from that right-hand side, well, it looks like it's pointed at that same point. It's pointed at actually that hole right there again, which we said has a y value of -2. So here the left-hand limit is -2. The right-hand limit is -2. So again, I could look at my graph, or I could just say, hey, you know what? I've got the left-hand limit, I've got the right-hand limit. They are the same, so that means that the two-sided limit must also be -2 here. Last thing I need to look at here, f of 3. F of 3, so that's just what's the y value of our function. So let's get rid of some of these arrows. The y value of our function here at 3. Well, here I have a hole, so I know that my function doesn't exist at that point, and there's no other point there at x equals 3. So we don't have a value of our function at x equals 3. So the only option we have here is to say that our function does not exist or is undefined here. So again, just really I want to emphasize that the value of the function and the value of the limit are two very, very different things. I would absolutely practice looking at left and right hand limits. I promise it's something I'm going to ask you about. I think it's a really, really good way to further understand and develop your understanding of limits. In the next section, in the next video, we're going to start to talk about properties of limits and how we can look at limits algebraically if, say, we don't have the graph.